Hello online viewers, welcome to our lecture video. In this lecture video, we'll be doing analysis of beam and we'll be covering the topic of what is beam, what are the types of loads acting on the beam, what are the types of supports on the beam, and how we can draw the shear force and bending moment diagram of the beam, and we'll also be talking about the sign convention involved while drawing the shear force and bending moment diagram of the beam. So first we will be answering the question, what is beam? So what is beam? So what is beam? A beam. A beam is a structural member designed to support loads at various points along the designed to support loads at various points along the member. And beam is a horizontal structural member. So we do not beam by a horizontal line, and it has certain supports at its end. There might be some intermediate supports at as well, and there might be various types of loads acting on the beam, and this original structure, remember, which supports all these loads acting on it, is known as a beam. So this is a simple definition of beam. Next we'll be talking about the types of loads, types of external loads acting on the beam. So as you can see here in this first example, there are three different loads acting on the beam: P1, P2, and P3. All these examples, P1, P2, and P3. These are examples of point or concentrated loads. While solving any kind of while drawing any kind of bending moment or shear force diagram, we need to convert each and every kind of load into the point load. So as you can see, P1 and P2 are point loads, and they act normally to the normal to the axis of the beam. As you can see, here is a point here is a point load P3, and it is acting at a certain angle theta to the axis of the beam. So what we do is we simply resolve the beam into its sine component and cosine component in order to solve the beam. So this is our first example of type of load, first type, which is the point or concentrated load. And as you can see here, the next example is our UDL, or simply which refers to uniformly distributed load. So why is it called so uniformly distributed load? So as you can see here, over a span of 2 meter from left to right, the force of there is a uniform distribution of force of 5 newton per meter. So if I move on over any section, over here, there is an uniform load applied of 5 newton per meter. So as I said before, solving in order to solve any numericals or any numericals related to beam, we need to convert any types of beam, whether it may be UDL or UVL, uniformly varying load, which we will talk later. We need to convert them into point load. So how do we convert uniformly distributed load into point load? So in order to convert uniform distributed load into point load, what we do is we simply multiply the value of UDL with over the span with its applied. So what we do is we multiply 5 newton per meter with 2 meters, and we get a value of 10 newton. So we get a value of 10 newton, and this load applies at the midpoint of its span. So for the midpoint, 2 meter divided by 2 equals to 1 meter. So in order to convert the UDL into point load, what we have simply done is we have multiplied the value of UDL over its span, and it acts as midpoint at a distance of 1 meter from the left, and a distance of 1 meter from the right. So now our third example of load is UVL, uniformly varying load. Uniformly varying load. So unlike UDL, it doesn't act equally over all the portion. So as you can see, as I move from left portion of the beam to the right portion of the beam, the magnitude of the force is increasing. Magnitude of the force is increasing. So likewise UDL, we have to convert UVL to point load as well in order to solve our numericals, in order to calculate our shear force and bending moment diagram. And in order to do that, what we do is, as you can see, this resembles a triangle, and this resembles a triangle, rather a right angle triangle. And as you know, the area of right angle triangle is given by 1/2 into base into height, and in order to convert it into point load, we apply the same formula, 1/2 into, it has a base of 2 meters and height of 5 newton per meter. This is 2 meters. So this if you cancel 2 and 2, we get 5 Newton. So in order to apply, in order to convert it into point load, we apply this formula of 1 by 2 into base into height, same as that of right angle triangle, and here we have its value in point load as 5 Newton. But unlike UDL, it doesn't act at a midpoint. It acts at a distance of h by 3 or x by 3. It acts at a distance of x by 3 from the longer side, from this longer side of the triangle, so which is 2 by 3 meters, which is here x at the value of x is 2. Here x refers to the span over which the force acts, so 2 divided by 3 is 2 by 3 meter, and it acts at a distance of 2x by 3 from the shorter side of the from the shorter side, which is equal to 2 into 2 by 3, which is 4 by 3 meters. 4 by 3. So as you can see, 4 by 3 plus 2 by 3 equals to 6 by 3, which is value of 2 meter. So now, so in this way we convert UVL into point load. Converting UDL into and UVL into point load is very important in order to calculate our shear force and bending moment diagram. So next we'll be talking about the types of support in the beam. So regarding types of support. So there are three types of supports. I think there are three types of supports on the beam. So now we'll be talking about supports on beam. Supports on beam. What are the different types of supports on the beam, and what are the reaction forces and what are the reaction forces produced in it, and what are the reaction forces produced on it. So there are three types of supports on beam. First is fixed end support. Second is hinge support, and third type is roller support. And they have different types of reactions involved in it. So firstly for the fixed end support. So this is a fixed end support. So what does a fixed end support basically does is it provides any type of particle motion. It prevents any type of particle motion. It prevents any type of particle motion, and it also prevents any sort of so what does fixed end support does is it prevents any sort of horizontal motion. It prevents any sort of horizontal motion, and it prevents any sort of particle motion, and it also prevents any sort of movements. So this is what fixed end support does. It prevents your any sort of horizontal motion, any sort of your particle motion, and any sort of your movements. So in order to prevent all these three types of motions, there is production of horizontal reaction, Rx. There is production of particle reaction, Ry, and there is production of movement in a z direction, which is known as Mc. So three reactions: horizontal, vertical, and in z direction to resist the movement. Three types of reactions forces are produced in a fixed end support. In a fixed end support. Next we'll be talking about hinge support. So this is what a hinge support looks like. So a hinge support prevents your horizontal motion, and your particle motion. So there is a production of particle reactions and horizontal reactions, Ry and Rx. Since it doesn't prevent any reaction movements are produced in it. So there are only two reactions, Rx and Ry, in hinge support. And in our final example of roller support only prevents particle motion. It prevents only particle motion, so only particle reactions, Ry is only one reaction is produced in roller support. So these are your types of supports on your beam: fixed end support, hinge support, roller support. We need to understand what are the reactions produced in it and how the reactions are produced in it. So next will be now we'll be talking about talking about how to draw the shear force diagram and bending, how to draw the shear force shear force diagram and bending moment diagram, and what are the shear and what are the sign convention involved. So firstly, let me talk about shear force and bending moment. So what are shear force and bending moment? So basically, so what are shear force and bending moment? Shear force and bending moment both are your internal forces. They are your example of internal forces, and they are your example of reaction forces. These are your reaction forces which are produced in the beam in order to in order to maintain equilibrium in the in order to maintain equilibrium in the beam in order to maintain equilibrium in the beam against your external forces. In order to maintain equilibrium in your beam on against external forces. So whenever external forces, which may be point load, UVL or UDL are applied on a beam, this type of forces are developed in the beam in order to maintain equilibrium So in order to simply define shear force is your algebraic sum of forces. It is your algebraic algebraic it is your algebraic sum of forces acting either on the acting either on acting either on left acting either on left or right side of the beam. Acting either on left or right side of the beam. It is your algebraic sum of forces. To be precise, particle forces. And regarding your bending moment is also your algebraic sum. It is also your algebraic sum, but it is your algebraic sum of moments. Moments means your multiplication of force and distance. Particle force and distance. Particular force and distance multiplication is known as your moments, acting either on left or right side of the beam. So bending moment simply means algebraic sum of your moments acting either on left or right side of the beam. So next we'll be talking about sign convention. What is sign convention for drawing your shear force and bending moment? Sign convention. Sign convention is very important. Is very important in order to calculate your shear force and bending moment diagram. So in order to know about your sign convention, you need to know whether you are moving from left to right, or either you are moving from right to left. Whether you are moving from left to right or right to left of the beam. So let's say this is an beam. If you are moving from left to right, if you are moving in this direction, you will have a certain sign convention. But if you are moving from right to left, if you are moving this direction, you will have exactly opposite sign convention. So let's say if you are moving from left to right, in this condition, you will take upward load as positive, while you will take a downward load as negative. This applies for the shear force as well. So if you have a certain section of a beam of force which tends to shear left side of the beam upward with respect to your left hand side, this shear force is taken as positive, while the shear force which tends to shear the right hand side of the beam downward with respect to your left hand side, this type of force is taken as negative. Vice versa while moving from right to left, if you are moving in this direction, it is exactly opposite. Upward load is taken as negative, whereas downward load is taken as positive. This is same for the shear force as well. Now for your bending moment, while you are moving in left to right direction, clockwise moment is taken as positive. Your clockwise movement is taken as positive, whereas your anti-clockwise movement is taken as negative. Similarly, while you are moving from right to left, clockwise movement is taken as negative, and anti-clockwise movement is taken as positive. So for your bending moment, positive bending moment is known as sagging. While negative bending moment is known as hogging. So for your positive bending is known as sagging, whereas your negative bending negative bending is known as hogging. Hogging. So what does sagging look like and what does hogging look like? So if you take a certain portion of the beam, so if a beam bends such that the center of curvature lies above the beam, so the beam has bended in such a way that the center of curvature of the beam is above the beam. This type of bending is known as positive bending or sagging. Or if a bend if a, or if a beam bends in such a direction that the center of curvature is downward. Center of curvature is a downward than the beam. This type of bending is known as hogging. So this is your sign convention of the beam. This is very very important in order to solve in order to this is very very important while calculating the shear force and bending moment diagram. You need to know whether you are moving from left to right section of the beam, or whether you are moving from left to right, or right to left section of the beam, and likewise you'll have your sign convention. So we have talked about sign convention as well. Now we'll be using all these examples in order to finally calculate shear force and bending moment diagram of a certain beam. So let me explain this with an example. So now I have drawn a certain beam. It has certain supports, and there is a point load W acting at midway between those two beams. It is acting at a distance of L by 2 from both the ends. So what I need to do is I need to calculate the shear force and bending moment diagram of this beam. So in order to calculate that, so first what I'll be doing is you need to follow the same steps. So what you can do is I'll be removing these supports. I'll be removing both the supports. This up here, and I'll be removing both these supports, and I'll be just showing the loads and reaction forces acting on the beam. In order to remove the loads, what I'll be doing is I'll be applying this is point A, this is point B, this is point B. I'll have to apply reaction forces in order to remove those supports. I have provided reaction forces of RA and RB. At both ends of the beam, and at point C I have my point load of W. So you can do this much. After doing this, firstly what I need to do is I need to equate what I need to do is, so as I show in my sign convention, I'll be moving from left to right portion of the beam, and while I'm moving from left to right, upward load is negative. So I need to do the same. I'll be equating in y direction. EFy equals to 0. So what we are basically doing is we're applying the condition of equilibrium. So as you might know, for the condition of equilibrium, upward forces equals to 0 and EFx is also 0. We will not be applying this because there are no any axial forces acting on the beam right now. We don't need this, so we'll be applying this only. EFy equals to 0. We'll be taking as upward forces as positive, as we are moving from left to right section of the beam following our sign convention. So if we so what are the upward forces acting on the beam? RA and RB. RA plus RB. Since this W, which is a point load, is acting downward, I'll be put minus W. So I get RA plus RB equals to W. This is my equation 1. So as you can see, there are only two reaction forces acting on the beam, and this point load is acting at the midpoint. It's acting right at the midpoint. So what I can see is RA equals to RB. This doesn't happen in every case, but in this case, since it is acting right at the midway, we can take these reaction forces, and there are only two reaction forces involved. We can take RA equals to RB. So what happens is RA equals to W by 2 and RB equals to W by 2. So I have calculated the value of RA and RB. This is my first step involved. Next, what I'll be doing is I'll be calculating shear force. So in order to calculate shear force or bending moment, what I need to do is I need to take certain sections from left hand portion of the beam while moving to the right. So what I'll be doing is we'll be taking certain sections and we'll be expanding that sections. So this is RA. I have taken a certain distance x, certain distance x at the right hand side of the right hand side of the beam as I'm moving from left to right. So what I'll be doing is I'll be calculating shear force at A. So shear force at A equals to 0 Newton. 0 Newton. No any forces, because right at A there are no any forces involved. There are no any forces being involved. So as I said at the definition of shear force, so as I said, shear force, as you can see here, shear force is the algebraic sum of forces acting either left or right hand side of the beam. So if I move at point A, so this is my point A, at left of A there are no any reaction forces. There are no any forces. So if there are no any forces, the shear force is 0. The algebraic sum of forces is 0. So let's say if I move a little bit right side, I'm moving from left to right, I'm moving little bit right side of A. So let's say I have moved at shear force at left of C. Shear force at left of C. So I have increased my value of x. Here is point C. I haven't yet reached point C, but I have increased the parameter x value, and I have reached a certain portion at the left of C. So as I said, the definition of shear force is algebraic sum of forces. So shear force at left of C becomes RA, which has a value of W by 2. At the left of C there is RA. There is a vertical force of RA which is acting upward. Since it is acting upward, we take it as opposite following our sign convention. So we have our shear force of W by 2. Now I increase the value of x and I move to C. I move right at C. So shear force at C is, I already have value of W by 2 minus W because at C W is acting downward. So since it is acting downward, we need to subtract this. I get value of minus W by 2. Then I slowly increase my length of the beam, and I reach to point B, and I reach to at point B, and at point B there is a vertical force W by 2 acting upward. So shear force at B equals to minus W by 2 plus W by 2, which is 0. It ends with a 0. Now in order to draw our shear force diagram, what we need to do is we'll first draw our horizontal line firstly. As I said, the shear force at A is 0. And shear force at left of C is W by 2. So it has a value of W by 2 until it reaches C. So as you can see here, the shear force value remains uniform because there are no any other loads. There are no any other external loads applied during this section until we reach point C. So it remains constant. So at point C it decreases to minus W by 2, and it ends, and it remains constant like over here, because there are no any other forces being involved. As you can see, no any other external forces are being involved, and when you move to point B, it ends at 0. This is our shear force diagram. We'll understand it more on our further tutorials where we'll involve our numerical examples. So do check all those videos as well. So now for a bending moment diagram. So as we similarly for our shear force diagram, as we took certain sections, we'll be taking certain sections for our bending moment diagram as well. So bending moment diagram. So bending moment at x equals to 0, which means at A mx equals to 0. So because at A the value of x is 0, we haven't moved any distance. There are no any reaction forces similar to this concept. Mx is 0. Now we move at bending. Now if we let's say if we move bending moment at x equals to L by 2, which is at C. Mx equals to, let's see, we have reached over point here. So let me again draw the figure. I have reached right over here. There is a point W being act. I have reached over here. X equals to L by 2. X equals to L by 2. So what is my bending moment right over here is, I need to see the forces acting at the left of the beam. So what is the force acting at the left of the beam? W by 2. RA equals to W by 2. So as you can see, with respect to this portion of C, this force tends to move upward in clockwise direction. So according to our sign convention, as I said, clockwise movement is taken as positive. So what we need to simply do is W by 2 into L by 2, which is W by 4. I haven't yet reached C. I haven't yet reached. I have reached at C. I have reached C at x equals to L by 2, and I am looking at forces left of it. So as I explained in the definition, I need to see the force left of C, which is W by 2, and in order to calculate this moment, I need to multiply force with the span, with the length, W by 2 into L by 2, which is WL by 4. Now I'll be calculating bending moment at x equals to L, which is at this end section. So as I reach at this end section, there are many forces being involved. There is a force of W by 2, there is force of W, and there is again a force of W by 2. There is again a force. We won't be looking at this force. So let me draw x equals to L. X equals to L, which is acting at a distance of L by 2. Setting at a distance of L by 2. So as I move at this point, we are calculating moment about B. We are calculating moment about B at x equals to L. So this force W by 2 won't be calculated. We'll be taking forces left of B. So this forces B won't be involved. In shear force it was involved, but in while bending moment diagram, this force W by 2 is not going to be involved. It has no role in it, because the length parameter has been involved. So at B, as you can see, there is W by 2, mx equals to W by 2 into L. It again produces clockwise moment only. As you can see, with this portion, if you fix this portion, W by 2 tends to move the beam upward, that is, it produces clockwise moment. But and here the distance has increased. With respect to B, the distance is L minus W into L by 2. Why minus? Because as you can see, with respect to B, W produces your anti-clockwise moment. It tends to bend the beam downward, and it is acting at a distance of L by 2 from B. So minus W into L by 2, we get 0. Our bending moment needs to end at 0. So in order to draw our bending moment, I'll be drawing my bending moment over here. So as you can see, here the bending moment is 0. So and it increases linearly at point C. So it increases linearly to a point of WL by 4. It increases linearly. So the fact you need to understand about shear force and bending moment is, if there are no other forces involved between those loads, the shear force remains constant. It remains constant, whereas the bending moment increases linearly. And after this, the bending moment decreases linearly to end up at 0. So this this value is WL by 4. The bending moment increases linearly, and as soon as it goes here, due to the effect of this force, it decreases linearly to end up at 0. So this is your bending moment diagram. So this was your simple introductory video in order to how to calculate your shear force and bending moment diagram. If you diagram, will be creating playlist of shear force and bending moment diagram, where we involve further more examples involving UVL, UDL, point loads, cantilever beams, etc. So in order to know more, do subscribe the channel, like our video, and if you have any comments, if you have any queries, do comment down below. And for your PDF notes, I'll be uploading all the PDF notes of all these lecture videos, so it becomes easier for you in my Instagram page, which link you can find at the description box below. Do like the page and follow our page. Thank you very much.